Sauce here. This is a video lesson on Pascal's triangle. I'm going to do something that looks sophisticated, and I'm not going to use a calculator or notes. I'm going to expand a plus b all to the sixth, which means multiply a plus b times itself 6 times. And I'm going to write it out in one go, the final answer all at once. It's going to be long, so I need to write small. It's quite a sophisticated expression, a binomial expansion, multiplying a binomial by itself any number of times. I followed a pattern. I didn't memorize it. I'm going to do it one more time. I'm going to expand x minus 2 to the fifth. See if you can catch on to the pattern before I explain it. X minus 2 all to the fifth is equal to So there are parts to that pattern. Let's take a look at what I did. The first thing I did in the pattern is I wrote out the x terms. The first term is going to be x to the fifth. And I created space to create terms of the expansion. I made space for the first x to the fifth, and then I counted down the powers of x until I got to just x, and then wrote a final sixth term without x. Then from there, I went backwards with powers of 2. The final term is going to be the fifth power of 2, and all the terms before that are going to be 1 less power of 2. Now I know the fifth power of 2 to be 32, and so when I went backwards through the terms that I created, I wrote it 1 less power of 2 to 16 to 8 to 4 to 2. Finally, what was the first term that I started with had no 2 represented, or this would be 2 to the 0, and that's why we don't see it. The third part of this pattern was that I put a list of numbers. Those are the coefficients. In this case, I put the numbers 5, 10, 10, and 5. The first and last terms don't have a number with them, or you could think of it as a coefficient of 1, which then didn't get listed. The final thing I did was I decided the sign of the term, whether it was positive or negative. And the first time it's going to be all positive because this first example was a sum. When you're working with a difference, then the sum of the term or the sign of the term is going to be either positive or negative. And the way you decide is it's the negative 2 that gets powered to create either a positive or negative number. So in the term that had a fifth power of 2, 5 being odd, it means that the negative 2 times itself 5 times will end up being negative. That's why we see a negative in front of the 32. Going backwards, the power of 2 is going to be even here, therefore positive, and then odd again, and then even again, and then odd. So the sign of the term is going to be negative when the negative has an odd power. That completes the pattern of the expansion. One mystery about this is, where did I get the values that were the coefficients? Where did I get the pattern 1, 5, 10, 10, 5, 1? Where did I get the pattern before of 1, 6, 15, 20, 15, 6, 1? Those coefficients were gotten from what we call Pascal's triangle, which is a pattern of numbers that I will generate follows a rule. Pascal's triangle literally looks like a triangle of numbers, and the top of the triangle are ones. And we can go and generate more rows in the triangle by adding the two numbers to the right and left above it. In other words, I need to put a number here to complete this triangle, and the number that goes here will be the sum of the two numbers above it to the right and left. Those two numbers are 1 and 1 to make a sum of 2. Now that I have a number here, I can create a number in the triangle that is the sum of 1 and 2. And there are other patterns that emerge. If we go down this side inside these ones, then it's going to be the sequence of integers. We can even add another row to this triangle. Going down this side to fill in these numbers will also be a sequence of integers. More inside the triangle, the number that goes here is the sum of the 3 and the 3 to make 6. So the 4 and the 6 combine to be 10, and then 10 again. 10 and 5 make 15, 10 and 10 is 20, then another 15. And if there isn't a number, we could think the number that goes here could be thought of as 1 plus something that's absent is 0, or just 1. Now, this is a triangle of numbers, and you can keep building rows off of it as you go. The row number, or the top row, is considered to be row 0. So the row of numbers below the top is then row 1. And we can descend through this pyramid, or this triangle, which we call Pascal's triangle, and the rows increase as we go lower and lower. The numbers that I used for the coefficients came from a row of this triangle. The numbers 1, 6, 15, 20, 15, 6, 1 is right here in the 6th row. How did I know to use the 6th row? Well, that's the power of the expansion. The 5th power of the expansion will have coefficients that come from the 5th row of this Pascal's triangle. The 5th row is right here. I know it because I can see that in this pattern, the row number is always going to be the same as the second number in the row. So the row number is 5, and I use these coefficients, the pattern 1, 5, 10, 10, 5, 1, which are the coefficients that were used in this expansion. We can generalize this. A binomial a plus b to the nth power has a pattern in its expansion. But we need a general way of finding these numbers. And that general way of doing it uses a c with two numbers before it and after it. The first number is what row it belongs to, and the second number is its position in that row. Now, these sequences of numbers start with a position of 0. So this here, that value of 10, comes from using this notation with a C, and before it, it's in row 5, and its position in that row, I have to count with a starting position of 0 from 0, 1 to 2. Again, that value of 10 can be represented with the notation 5C2. Row number 5, position number 2, has a value of 10. Let's do that one more time. This value of 15 is in a position in the Pascal's triangle, which we can give to be the notation 6th row, C, position number 0, 1, 2, 3, 4. Why C? C stands for combination. It's shorthand for combination. And the reason why the C stands for combination for positions of numbers in Pascal's triangle is because Pascal's triangle is used for much more than binomial expansions. Pascal's triangle is used in the mathematics of combinations and permutations, which are topics typically taught in a statistics course. So there's many applications of Pascal's triangle. It's quite profound. But if we're going to use it here for a general binomial expansion, a way to power a sum or difference of numbers and just write that expansion out very quickly, the pattern goes like this. First, the A, or the first term, is going to decrease in exponential value by 1 each time until it has an exponential value of 0, which turns into 1 and won't be represented. And then the second term in the expansion, which we're calling B, has the same pattern but in reverse. In the last term, we'll have b to the n. And in the first term, b will be to the 0. So before it gets to 0, it's at 1 and then squared. The coefficients then are going to come from Pascal's triangle. The first term will have a coefficient in the nth row in position 0. So the second term will be in the nth row, but position 1. And this term then will be in the same nth row with a position of 2. Till finally we get to Pascal's triangle number position in the nth row and the nth position. Last thing to add is that this is the sum of terms. And if these terms need to be negative, it will be because the b value is negative, and the sign of the term will be determined whether it is an even or odd power of that negative value b. This pattern on the expansion is what we call binomial theorem. And it takes some practice to use, but is very powerful when you do.